we are going to have a look at the probability factored form theorem. So, what are our assumptions? Let A1 through n be such random events that the probability of the intersection ranging through 1 to n less 1 of AI is greater than 0. As we know, probability is a positive or non-negative function, so we could effectively replace this by the requirement that it is non-zero, but it doesn't matter. If this is satisfied, then we claim that the following identity holds. So, we have the probability of the intersection of the random events, and we say that it is equal to the probability of the conditioned event of an under the condition of a1 intersected with a2 all the way until an minus 1. And now we continue times the probability of an minus 1 under the condition of a1 through an minus 2, and we continue by analogy until we arrive at the probability of the event a2 under the condition of a1 times the probability of a1. The proof is, of course, trivial. Proof. We shall lead the proof by induction, but before we do that, we first need to establish one fact. We say that from P, the probability of A1 intersected with A2, A3 until an plus 1 being greater than 0, it follows that the probability of the intersection ranging through 1 to k of the events AI, where k is smaller or equal to n minus 1, is greater than 0. This follows from the fact that probability is a monotonic function, and of course, with the decreasing k, the argument is increasing, it is becoming bigger. And since something smaller is greater than 0, this, of course, by the transitivity property, is also greater than 0. Now, we can get to the induction. So, by induction, by mathematical induction, suppose that n is equal to 2. It's an induction on n. And then the claim holds trivially, since P of A2 intersected with A1 is equal, by definition, to P A2 under the condition of A1 multiplied by P of A1, the probability of the condition. Why? It is quite simple. The reason for it is that P of some event x under the condition of y is equal to the condition of x intersected with y divided by the probability of y. As you can see, we can get this identity easily from here. Now that we have verified the initial setup, we can move on to the induction step. So we assume that the theorem holds for all n, for all k smaller or equal to n minus 1, and we wish to prove the claim for n. Now, P of A1 intersected with A2 intersected with etc. until AN, of course, can be written as the intersection of the intersection ranging through 1 to n minus 1 of AI intersected with AN. Now, we use this identity, or rather this identity, but tacitly also this identity, to obtain the following. This is equal to the probability of P A N under the condition of I ranging through 1 to n minus 1 of AI multiplied by the probability of the condition minus 1 AI. And, of course, we can apply the induction step on this factor. And thus, we obtain the claim. Because by the induction hypothesis, this is equal to the probability of AN intersection A1 through n minus 1 AI times the probability of AN minus 1 under the condition of AI, AN minus 2 AI, and so forth, until we arrive at the probability of event A2 under the condition of A1 times the probability of the event A1, which is precisely what we wanted.